So the next section here is switching concepts. And switching concepts, communication at layer 2 concepts is really what we're talking about here. So in the switching process, the frame arrives at the port. It's placed into an ingress queue, and these devices do use queues, lines. A queue's a line that does that thing, and each queue has a different service or priority level, quality of service. We're kind of jumping ahead. We'll do quality of service, talk about quality of service and how it gets configured, but we can have multiple levels of priorities, kind of like on the interstate. When you go out there, we have 2 levels of priority. Those of us who are stuck in traffic and those who can get into the carpool lane, which generally is going to run a lot faster. So the same thing happens here. We have queues, voice over IP phone calls. We don't want phone calls to fail. And so it's going to get a real high priority. You know, one of the things, emergency phone calls, you want them to always go through. So the phone, the voice is going to get a high priority. Video, we don't want it to be jerky. We want nice, smooth video so that we can watch the movie or participate in a class over the internet or something like that. So it may get a little bit different priority. And then the regular data, when we download a web page, okay, so it gets delayed by 10 milliseconds or 40 microseconds or whatever else. Probably doesn't make a whole lot of difference to us because they tend to be pretty static when we do those things. So each queue, each level of service is going to have a different priority in order to determine how much, how long it gets to use the data path to do these things. Look up the source MAC address in CAM update, the timer, the address, and the port. We're going to look up the source MAC address and see if it is there. If it is not there, we're going to put it into the MAC address table. If it is there, reset the timer because that address has been reused. And is the port correct? Did we move it from one port to the other? And if that's the case, and if it's already there, we'll reset the timer and just simply move that MAC address to the new port. The destination MAC address, the forwarding address, and the egress queue are found. How are we going to get there? And the forwarding, once this addressing is determined, and we have the MAC address table, all of the forwarding happens using what are called ASICs, application-specific ICs. And the application-specific ICs don't use the processor of the device, the CPU and the memory, in order to be able to do the processing, because the ICs are going to be significantly faster than the CPU processing could be. So each of the steps that we've gone through to get into the switching areas that we are, to build the switching areas that we have been to speed up the process, speed the process. A bridge, we looked at that, talked about it a little bit, and you're probably not going to see a bridge, but a bridge was kind of a rudimentary switch, or a switch was an improved bridge that separated based on MAC address. A switch separates based upon MAC address. Kind of a multi-port bridge. A bridge used software, so it's going to be slower even if we actually are using multiple MAC addresses on each side to try to reduce the traffic on the different segments that go on with it. But the examines the CAM for the destination MAC addresses, and it forwards the address, and if the egress queue is found. If it doesn't find it, it floods, and it floods broadcast traffic, unknown unicast traffic, and that was what we had in the demo. We had an unknown unicast, unknown because it didn't know where the MAC address was. So it had to flood it out, all of the ports except the port that it came in on. The broadcasts are always going to be flooded out because a broadcast by definition goes to everything that's on that IP network. So it's going to flood out or broadcast out or forward out all of the ports, except again the port that it came in on when we do these things. Multicast addresses are also going to be flooded for these things. It's not flooded back onto the interface on which it was received, all the ports except the port that it came in on. Security and quality of service access control lists are applied. We have the TCAM, the ternary content addressable memory. We've looked at the MAC addresses. The TCAM takes into account the other qualities that can be applied here, like the quality of service, and maybe any access control list that we would have applied to it. We rewrite the MAC address if needed. And it says next slide. I want to go through a scroll and then we'll go through the automated of the rewrite. There is going to be some frame rewrite in these things. Then we have the egress queue. Each has a different service or priority level. The queues, the lines, how much priority does each of these things get? And all this queuing is done internally for the devices themselves. The frame rewrite, and let me do a probably pretty bad scrawl, but let's set up some devices, and we'll use circles for routers, and we'll use squares for switches and computers. So we have a switch here, and then we'll have a computer down here and a computer down here, and we'll connect all of this stuff together. Let's see if we can do a straight line here to connect all of this stuff together. I have this straight line drawer, and I still can't draw a straight line. So we're connected together, and we're not worried about right now IP. Well, we'll worry about IP addresses. Well, not what they are, but that we have them in the whole data packet. We're going to have the destination MAC, the source MAC, the destination IP, and the source IP. So in this, let's say its MAC address is A, and this one's MAC address is B, C, D. Each interface is going to have a MAC address. E, F, and they're hexadecimal, so now we're going to have to go with AA and AB for these things. If I'm going from, and let's say this is 192.168.1.1, let's do, yeah, and I'm going to 192.168.2.2, I'm going to make this 1.2, because this is going to be 192.168.1.1, 192.168.2.1, the default gateways. Default gateways by convention are the .1 addresses. They don't have to be. They can be anything that we want them to be. 192.168.3.1 and 192.168.3.2 when we have these things. So I want to go from 192.168.1.2 to 192.168.2.2. The routers will have the routes, so they'll know how to get there. The most efficient way to get there using their metrics and using the routing protocols to share route information. When I do this, we're going to go through the ARP process, and say we'll get the ARP process here in a little bit. We'll look at it and ARP tables, but what we need to determine is the MAC address of the next device. And I put the router or the switch in here. The MAC address of the switch only is significant if we're going to the switch. If we're going through the switch from one to the other, like we're going from the computer here to the default gateway of the router, the only thing that matters is the next device that we're connecting to. This just becomes a connection point, a collection of all of the cables that come in that connect them together when we go there. So the the source, or the in this case, the destination, not a very good D, still not a very good D. The destination MAC address will be C, because the next device is going to be this router. The source MAC address will be A. The destination IP address will be 2.2, and the source IP address will be 1.2. So we have the source MAC, the destination MAC, which goes first, the source MAC, the destination IP, and the source IP. When it gets to this device, we got to rewrite the frame. It's going to change. The world's going to change a little bit. I thought somebody said something. It's going to change a little bit. So in this case, the MAC addresses are going to be rewritten. To go across this section here, the destination MAC is going to be E. The source MAC is going to be D. The IP addresses don't change. The destination IP is still going to be 2.2, and the source IP is still going to be 1.2. So now we get to this guy. We get sent to E. We got to rewrite the frame again, rewrite the MAC addresses again. So in this case, the destination MAC is going to be AB. Get that down here. The source MAC address is going to be F, the interface that it's leaving from. The source IP, or do the destinations first. The destination IP is going to be 2.2, and the source IP is going to be 1.2. So the IP addresses stay the same. The MAC addresses get rewritten. And going back to when we looked at the frame itself, at the end there we had the FCS, the frame check sequence, which is a CRC. You may see it as CRC, cyclical redundancy check, which was a hash. We looked at a hash and what happens when we change anything that's being hashed. Well, the whole hash situation changes. So the frame check sequence has got to be changed at each of these things, and it will be checked to be sure that nothing changed in here, that it's the same going up here, that nothing changed in here. I'm not doing that very well, am I? Nothing changed in here, but it gets rewritten. So we have frame rewrite. Frame, F-A-M-E, rewrite. And in the frame rewrite, the MAC address gets changed, but we're also going to have some things we haven't talked about. Hop count. We saw a hop count yesterday, I think, when we looked at one of the Wireshark. So we're going to have to change the TTL, the hop count, the TTL. The time to live is going to be decremented as it goes across these routers. The frame check sequence is going to change. What else might change? But the MAC address certainly will change, and the frame check sequence has to be rewritten each time too, so that when we get to one of these devices, it doesn't show up and say, "Hey, you just uncreated or modified the whole world for this thing." In this one, we're going from BB, and we're going in this direction. So the source and destination MAC addresses for this thing. Anybody, what's the source MAC address? That's pretty easy, right? BBB. And the destination, and these are, yeah, I get it, they're backwards. The destination should be the first one that gets there. So BBB, the destination is 111, which is this guy up here. The switch has a MAC address, but we only use it. It only is significant if we're connecting to the switch. We're going to telnet to it or SSH to it in order to do configuration of it. We have to find that device. So in this case, when we're in the switch, the switch, everything's just connected through the switch. It's a pass-through, a connection point. The source is still going to be BBB, where we came from. The destination here is going to be 111. Same thing when we get up here. Now, when we get on the downside of the router, the source MAC is going to be 000, and the destination MAC is going to be AAA. Same thing when we get down here to do these things until we get from one location to the other location. So frame rewrite happens with these things, and we have to account for that when we do that. Flooding and forwarding, I think we've probably already done a lot of this. Flooding, if the destination MAC address is not in the table, the switch can't identify the outgoing interface. So it floods the frames to all the ports except the port that the frame came in on, the receiving port, to do these things. Ensures that the switch does not arbitrarily throw away unknown traffic. I don't know where it goes, so it's going to flood it out. It may not go anywhere. It may, in fact, be traffic that doesn't do anything for us. But instead of throwing it away on the switch, we'll go ahead and forward it out or flood it out. Flooding is a term that you will hear for going out all these ports. Forwarding is the term we'll hear for it going out a single port. So it gets flooded and the host replies. The switch creates an entry for the reply based on the source MAC address. What we hopefully saw in the demo a little earlier in this. Forwarding, if the destination MAC address is in the table, it sends it out only the associated port. And this is one, if we didn't have the dynamic changing and we had, we moved something from one to the other, it gets sent out the wrong port. So we have to have the ability to allow the switch to determine if the ports changed for that particular MAC address. Because if we didn't, and if we didn't have the dynamic, if we didn't have the timing issue with these things, the timeouts, then we get in a situation that we really would overfill the MAC address table, and we might have a MAC address on multiple ports. We can have multiple MAC addresses on a single port, but we don't want to have the same MAC address on multiple ports, because then the switch kind of gets confused, doesn't know where to actually send the information to. There are going to be three types of switches that have existed over time. And when you say, what kind of switches do we have today? I'm going to say, it depends, and you have to read the documentation. A lot of them are configurable to these three different types. The first one is a store and forward. It takes the entire frame. It checks the CRC here. So we have CRC, cyclical redundancy check, FCS frame check sequence, kind of interchangeable terms. Think of them as hashes to determine if anything has been damaged in this thing before the frame is forwarded. So in the store and forward, the switch gets the entire frame, runs the CRC. If it's damaged, if the frame's damaged, it drops it. Say, well, that's a problem then. Will it not get there? The answer will come when we do TCP. We did the three-way handshake, and we said that it is a reliable protocol, a connection-oriented protocol, different terms that we use for it. It asks for resends for data that's not acknowledged. So if it gets dropped in one of the switches, TCP will then take over and say, hey, you need to send that one again to do this. It ensures that the frames with the errors are immediately flushed, and this is going to keep us from sending the bad frames and taking up network bandwidth, network throughput, data rate, network resources by sending bad frames for these things. The next one is we want to make them faster. And what it does is it's called cut-through switching, and as soon as it reads the destination MAC address, and the destination MAC address is the first one in the frame, it starts forwarding the frame. it's going to be much, much quicker, but we have absolutely no error checking in this one. It's going to be faster than store and forward. Store and forward is going to be the slowest of all of them. Cut-through switching is going to be the fastest of all of them. But cut-through switching has no error checking at all, so we may be forwarding bad frames through one of them. Kind of a compromise, fragment-free. And I think one of the slides said yesterday that most collisions occur within the first 64 bytes. Most errors occur within the first 64 bytes of the frame. So the switch combines the error checking of the store and forward with the fast forwarding of the cut through. And after the first 64 bytes are received and checked, and if it's error free, it's going to then go ahead and forward it to the destination MAC address. So 3 types: store and forward, cut through, fragment free. Store and forward, slowest; cut through, fastest; fragment free, kind of a compromise between the speed and the reliability. We have here, and this is some of the commands that will be used in a couple of labs. There are some labs coming up, and what I like to do is consolidate them because we have 5 minutes here, 5 minutes there. Instead of doing that, consolidate them into like an hour and a half or something like that, so that you can get on them. And I think that in the software, you know, a 5 minute lab, you're probably not even going to get it loaded in 5 minutes in order to do that. So what I have done is we got a page here in a little bit that has a number of the labs consolidated into a lab period. So some of the commands here: show interfaces, and we can look at some of these. Show MAC address tables we've seen, show version we've seen, but we can go back and look at some of these commands here. The only other one I think that we haven't actually, we did see the show interfaces too, but some of the information that is on these things. Show interfaces, and then if you use the question mark, Ethernet, fast Ethernet, gigabit, we have to specify. If I just hit the enter key, it's going to show me all of them. So if you want to see all of them, more on down the line, we can do that. And some of the information here: line protocol is up, connected, hardware is LANCH, the address, the burned in address, the MAC address for this interface. The bandwidth is 100 megabits, 100,000 kilobits per second. We have delay. Reliability, 255 over 255 is a good reliability. Load, encapsulation, the keep alive here is 10 seconds. It's full duplex, 100 megabits per second. Input flow control is auto. So the things that you can see, and it goes on and on and on and on and on. If you want to get out of this, the escape key will break these things. And I could show a single interface. Let's try gig 01. Gigabit 01, when we do that full duplex, 1000 megabits per second. Same thing, burned in address. We have the MAC addresses, and they're all going to be related. This is 000CC. And if I go back up here to 000CC 5403 and on down the line, if you added these up, we would get up to 5406 is for fast Ethernet 06. And when we get to the gigabit, it was 5419. So they kind of increment based upon the port number that they use for these things. The MAC address table we've looked at. Running configuration file we looked at earlier. Show version. Actually, show version is an interesting one to look at, because that's the one that had the show version. The flash simulated non-volatile configuration memory. It says it's got 24 fast Ethernet 802.3 interfaces, 2 gigabit 802.3 interfaces, the motherboard assembly, the hardware information, configuration information that is available on this thing, the model number of it, system serial number that you may need to for some modifications if you're going to upgrade in some cases, add features to it, and then this generally goes with routers when you do that, but we can change from one to the other, but we have to know the system serial number so that Cisco knows which of the devices that we've upgraded when we do this thing. The ports here, it's the switch image, and this is the iOS image, the 2960 LAN base image, the version 12.2. The configuration register, which we talked about a little earlier, it's a little bit different look here than we had the 2102 and the 2142 were the two big ones in the routers. The configuration register, a little bit different look in the switches than in the routers. But the show commands, and these are things to try out. What do I see when I see these things? Show version, because you get a question like, okay, what command do you use in order to see how many ports are on the switch? And we saw there that there are 24 ports, and we use the show version command, or to find the MAC address or whatever else that you do. And this to me is where doing the labs becomes really significant for these things. You have a 5-minute lab here, and then two 5-minute labs, and then configuring the basic switch operation. I think that after we do this one, we actually will hopefully get into some of the labs, and hopefully they're working by now. The system dialog, and this is the setup, the startup, an interface mode, system configuration dialog, an interactive mode to perform initial steps for switch configuration. Appears automatically when a switch is powered on for the first time, or NVRAM does not contain a configuration file. And go back to, we looked at the configuration register. One of the things said, hey, look to see if there is an NVRAM, a startup configuration file, and if there is, loaded. If there's not, then we go into this setup mode here. Enters the switch setup mode and prompts the user to enter some basic switch configuration. I want to do that here in just a second. Yes, accepts the input. No, loads the basic iOS into Flash, and request confirmation to save the settings, and then the iOS saves the configuration file into NVRAM. And I think that you have one for that too. I'm just going to use this one. We'll go down here and bring up, and I'm going to bring up a layer 3 switch because I think it will work right. And I'm going to cheat. I'm not going to put in my computer. I'm going to use the CLI tab, which I'll keep emphasizing ain't real. It's just there for convenience for doing these configurations. So this one doesn't have anything, a brand new switch. You saw that, we just bought it, just drug it in here. What's going on with it as it's loading, some things that you can look at. We have the post, the power on self-test, the ASICs, the application specific IC tests go on in the startup. Get the product information here, and the cryptographic disclaimers. You can't export it to some places. Require assistance. Export at cisco.com in order to find that out. Some of these things, and that's changed a little bit over the years, but not entirely. So you can't really export everything. A lot of it you can. The Cisco C3560 24 port switch, the processor that is in it, the hardware specifics here in the startup, and then the switch image. The same thing that we had basically with the show version command. And then it says, would you like to enter the initial configuration dialog box? And let's say yes, just because we can. Would we like to enter basic management setup? And we'll say yes. Enter the host name for this switch, and we'll say CCNA L3 because this is a layer 3 switch. enable secret. Oh, this is something we haven't talked about, and we will after we do this. This is the called the enable secret password, and I'm just going to use secret so that I don't forget it, and enter the enable password. We have two of these, the secret and the password. Enable the virtual terminal password, and I'll do password. And we're not going to do SNMP management when we do this thing. Enter the interface for the management network. The only one that is available for that is VLAN 1. The management network has to be a layer 3, has to be a NIC, an IP. This is a virtual NIC, but the VLAN 1, here it's administratively down, and we'll say VLAN 1, configure an IP address, and we'll say yes. Configure 192.168.5.2 for it, and it automatically, based on the address, picks a subnet mask for me. And now we get into the what do we want to do this. We can go back to the prompt without saving the file, return to the setup without saving the file, or save the file. And the default here is 2 to save the file. If you want to take the defaults, all you need to do is hit enter for this thing. So you can see that the name changed, and I do enable, and now it's asking me for a password. And secret is the password. I'm going to go back out of here. If you get out of enable, you do disable. Do enable. I'm going to use the enable password, P-A-S-S-W-O-R-D. You just have to trust me that that's what I typed in. Doesn't use it. If I have both the enable secret and the enable password configured, I have to use the enable secret. It's the only one that's there. If I do a show start up config now, it's there, and the passwords are here. The enable secret, the 5 here says it's an MD5 hash. So this is the MD5 hash for the word secret. The enable password is in clear text. The reason it's in clear text because up here we have no service password encryption as part of the default configuration of this device. The reason is that it's very weak encryption, and I think that they just decided it wasn't worth the effort to do that encryption. And we can go on down the other things that we configured here. We did an IP address, and we named it. We did the VTY04, VTY virtual terminal, the telnet terminal, the SSH terminal. We have a password here, and then we have a login. The password is password. If we go into the configuration mode, just to see, and we'll do this again, and do service password encryption, and use the do command, and we'll do a show run. It encrypts those. This is type 7 encryption, and it is a weak encryption. You could take this and go on the internet and crack Cisco encryption or something to do a search for Google and crack this right then and there with no effort when you do those things. So the setup file, the way that we do that, let's see, if I do end, we'll go back here. End goes back here. Exit, of course, I'm only down up one layer, but exit goes up one layer at a time. End goes back to the privilege config file, privilege configuration prompt, the privilege exec mode. I'll get there, but that is the setup process, and I think you have a lab to do that. Once you've done the lab, hopefully you're never going to have to do that again, because you would be able to go in here and go into config T. And what we did the do the host name. We could change the host name. Let's do CCNA L31. L31. And we can change that immediately. So it changed it. We could go into the interface VLAN 1 and do an IP address of 192.168.6.6.2 2.9.0, and then I'm just going to give it the no shut command just in case, and change all of that thing. We can do the same thing with the passwords. Enable secret password. or the enable password, or the VTY password. So N is going to take me back. If I do a show run here again, then we've changed the IP address to the 6.2 from the configuration. And the reason I do that, yeah, you can use that setup. It doesn't really do a whole lot for you. And by the time you finish doing the labs today, you're probably going to be able to do all of those commands. The secret here is that it shows up if you don't have a startup config file. If you have a startup config file, it's going to go right past it. So you don't have to worry about what goes on with it. The command reference for this thing, copy running config to the startup config file. When we make configuration, say, oh, what's the big deal here? If you got one or two configuration commands, and again, I think I probably said that, and I'll probably say it multiple other times, not a big deal, but let's say you've got 200 or 300 lines of configuration. You probably want to save it so that you don't have to figure out what those 200, 300 lines are and type them in again. So it's going to save the configuration file. The write command or WR command is going to do the same thing. So you can either use copy, run, start, and run, the only thing that starts with run is running config. The only thing that starts with start is startup config. So you don't have to type running config and startup config. You can use copy, run, start, or much simpler, use the write command in order to do that. Enable, we've got that, goes into privileged exec mode. N exits the configuration mode. Ends and exits the configuration mode. N brings us back to the privileged exec mode or the enable mode. Erase the startup config file is going to make it go away if we don't want it anymore. Config T we've looked at. In the IP addressing, in the switch, we did an IP address on this thing. If we want to go off of the network, we'd have to use an IP default. Let's see, IP. Yeah, default gateway. You got a default network, and that's why it wouldn't complete for me. I wanted to see. Default dash gateway 192.168.6.1. It is configured separately from or with a totally different command than we use in the IP address. And we kind of get used to using the Windows where we have everything there together. If we do manual addresses, we have all those things, ping and show, and then the no shutdown or the no shutdown for the interface itself will bring the interface back up. Shutdown brings it down. Again, generally in Cisco, the no, and generally it's like, I can't think of an example where it doesn't work, but the no in front of the command undoes something. If you want to undo something, and I keep switching back and forth for this thing, let's say that, let's do a do show run, and let's say host name here. What I can do is copy it and go down here and do a no, and then paste it. And I don't know what's going to happen here. No host name, multi-layer switch, and now it comes back to whatever the default is. It changed it immediately. It took it out. So no in front of the command, and you can copy and paste them out of the running config or the startup config file in order to undo them if you want to do that. And copy and paste, everything that helps me avoid typos, I'm all for. And this is another 5-minute one, 10-minute one when we do these things. This is something, we have syslog here, system logging messages, and you can't really do any analysis on the Cisco device because we can't run software there. We can't run any analysis software on it. So again, it's the a protocol that does these things. It logs things locally, and a lot of time it's going to be in memory, volatile memory. And we lose power, we lose something, and the logs go away. What we want to do is to consolidate them into something like this. This is a free syslog server, Kiwi, free version, goes through this thing. And it will give us the logging information. Not a whole lot here. I've got some down here. I get some debugging so that I can just get a lot of stuff in here for what goes on. And the debug, as we saw, is what actually is taking place on the device itself. And this is some routing that's going on. Routed via the FIB, the forwarding information base. Doesn't mean anything to you right now. It may mean a little bit after we do routing, but what is actually happening. What we're looking at now is how we get the routing, the logging from one location to the other. Syslogs are useful in troubleshooting problems. And again, with this syslog server running on a device, could be running on a Windows machine, could be running on a Linux machine. And I think that syslog is native to Linux. I'm not sure about that, but somewhere in the back of my mind it's there. But we can run these things and collect information. We can collect information from multiple devices. We have the host name here, and that would help us in analysis of what went on if we'd been attacked on the network or something like that. What happened first, or what is the sequence of events that goes on with this thing. Handy thing that goes on with syslog, because we have the time and all of the other thing that goes on with it. The show logging command is used to view the current buffers. Now let me bring this guy over here, and hopefully we'll be able to see it. It makes changes for me. This is GNS3, and I've made this console bigger. This is the infrastructure. This goes to the cloud. The cloud connects to my local network, connects to the physical NIC of the device it's in, and allows me to now put this router on my network. So what I want to do here, and it's getting a DHCP address, and let's look at that real quick just so that you see what it looks like, because I've seen this one come up. And how do we get a DHCP address on here? It's just IP address DHCP, and here what kind of address we have DHCP, and up in the show IP interface brief is what we always want to see with these things. So what was that command that we talked about there that we did a show logging? Let's see if I can make that work here. Show logging, and that's what's going on this thing. The console level, the flushes, the active filters, what goes on with the system itself. What we want to do is to configure logging LGG, logging, and then the commands here. One of the things here is the host name, or ABCD, the IP address of the logging host. That's going to be where we're going to go, and it's going to be 192.168.1.27 is the device that we're logging to. The other thing that we need to do is to do a logging trap. In the logging trap here, we have these severity levels, and that's what's in that table in the slide. The severity level that we use, and what this says is, do we want to see everything, or do we just want to see things that maybe be important to us? You know, warnings, and generally severity level 4 on up, warnings. If we wanted to see it, we could say severity level 4, or we could type in warnings, and that'll give us the 4, the 3, the 2, the 1, and the 0. The 0, the emergency system is unusable, has always been one that intrigues me, that if the system's unusable, how's it going to send you a log message? But it is one of the severity levels that we have here. So if we don't have to specify all of them, we can specify one of them, and then everything that is more severe. I'm going to go ahead and use 7 to do this. It's a trap. I'm going to say trap, and then you see we can do severity whatever. And let's just use debugging to do that. The reason I want to do debugging is maybe it will send me something here. Yeah, send me something to my server that I just configured. What it is the command line interface initiated. We started logging on this thing. So let me get rid of the router and bring the syslog server back over here. So at 11:02:09 on 6/16/2020, that'd be today and right now, we have a local 7, an info type of severity level, an informational severity level, which is level 6. Says that logging, start, stop, logging to host 192.168.1.27 started. It was initiated from the command line, and we were at the command line, and we initiated it, and that's exactly what happened. So logging can be sent to a syslog server, and we have to specify. You don't just say logging, you have to specify which severity levels that you want sent to you. So the ones here, the emergency, alert, critical error, what do we want to see in the logging itself? We don't have to see everything. This is one, if you guys can come up with a good acronym, I guess, in order to configure this thing, let me know, because I've never been able to come up with one. Anyhow, let's continue with a couple more topics to do here, and then hopefully get into some labs. Switches and security, and we did this, I think, most of this when we just demonstrated, when we looked at the passwords that are available on the switch. We can set passwords. The enable password, which is the unencrypted one, that is unencrypted because the default for the Cisco devices are no service password encryption, and these are service passwords. The enable secret password, which was the MD5 hash that had the 5 next to it. And then service password encryption, we can turn it on, but again, the reason it's not on is because it's very weak encryption. The only thing it would do for you if somebody was looking over your shoulder while you were on the console, they wouldn't be able to discern the enable password if you were using it. Should be using the enable secret anyway. This is one of the things that you're going to find in Cisco. We're going to do a protocol called CDP, Cisco Discovery Protocol, in a few minutes. And it's one that, they did this. They did the enable password, and then they decided they had to hash it. So they did the enable secret password. They made it override the enable password, but never took it away. In the CDP, we're going to have a Cisco proprietary as well as a standard when we're discovering devices. And you're going to find that happens a number of times. And a lot of times Cisco has this concept or develops this process. It's kind of out in front of everybody. It becomes a proprietary process, and then they say, oh, that's a pretty good idea. Let's develop a standard. They incorporate the standard, but they don't take the proprietary out. So why do we have these two passwords, which kind of don't make a lot of sense? Use the enable secret password, the MD5 hashed one. The privilege levels that we have are 0 to 15. So what we have, one is the user exec mode, the greater than sign. The 15 is the privilege exec mode, the pound sign, when we do these things. So we can go from like 0 privileges, no privileges, limited privileges, to unlimited privileges based on the privilege level. Nothing's really assigned to the in-betweens. What we can do, and this is beyond the scope of CCNA, what we can do is assign explicit, specific commands and define them for other privilege levels. And when we go into AAA, we will create users, local users, and we will or can assign them a privilege level. So in that case, we could associate specific commands with a privilege level, create a user, and then restrict what they can do. It's not as clean as you would have in a Windows or a Linux environment, but you do have the capability to do these things. Password checking, authentication methods lists, and we'll do AAA, and we'll talk about the login versus login local. And I can tell you, login versus login local. Login says you got to have a password. Login local says that we're going to use the local database that we will create in order to do that. Authentication methods list. What method are we going to use? And we'll do that in more detail, other than saying, yep, this is what we do. We will configure that when we do the AAA, the authentication, authorization, and accounting section. And we'll also do .1x. Port security kind of becomes its own entity, and we will configure that next week when we do the security portion of it. .1x, 802.1x is a port authentication protocol that you have to actually log in order to activate a port. Another one that we'll talk about, look at, try to do a demo in the security portion of it. The address resolution protocol, ARP, is one of those protocols, or is that protocol that is pretty simple. And it's so simple that it will take an answer to a question that was never asked. It is one of the methods that man-in-the-middle attacks take effect from. So that you send an ARP reply, and I've got ARP and I've just filtered on ARP here, but this is an ARP request. Who has 192.168.1.90 till 1.27? So now we get a response going back to, and you notice that the request is a broadcast. The reply here is going to be a unicast. And let's go back up and look at the destination MAC address here, broadcast. The destination IP address, source, a destination IP address. We have the destination. We don't have the IP address because that's what we're trying to relate here. We have the MAC address. The destination MAC address is going to be the broadcast. Who has, everybody who has 192.168.1.90. Who has, and is asking which MAC address is there. When we go to the reply, the MAC reply, it's a unicast. It goes to a single device. The destination here is going to be whatever the source MAC address here was on the request. So we have the ability to create these ARP tables. And you can see the ARP table. Let me get a command prompt up here. You can see the ARP table by using the ARP-A command on this. And let me go to this again is the real one, the ARP-A 192.168.1.1. What's the MAC address and how was it discovered? Dynamic. Using the ARP process. We have some statics down here. We have the 1.255, the broadcast IP address, and here we have the broadcast MAC address. Let's see if we can make that a little bigger, a little easier to see maybe. But what the ARP table, and these are things that time out. Each operating system is a little bit different on the timeouts, but they do time out. And it's the same thing we talked about in the MAC address. If it gets reused, it gets reset. If it doesn't get reused, it's going to time out without being reset, obviously. But we have the IP addresses and the MAC addresses that are within this. You notice they're all 192.168.1 addresses that are within this particular broadcast domain. That's where we're going to use these addresses now to communicate from one device to the other device within that broadcast domain when we do those things. So the ARP dynamically maps IP addresses to MAC addresses, enables the host or router to find the MAC addresses of a destination. The host store the MAC addresses in the ARP cache or the ARP host table. We saw the ARP cache, and that's what we were looking at. And again, they do timeout. They are cached. So we send the ARP request address for whatever. The ARP request is going to be a broadcast. The ARP reply is going to come back, will be a unicast. And then we're going to, this one over here, the MAC, the ports, the MAC addresses are going to be associated with the ports, obviously. The ARP table will then associate an IP address with a MAC address that we just saw. And I think this is the last of the topics that we have before we do labs. Maybe not. Well, the discovery protocols are going to be two of them. The Cisco discovery protocol, the Cisco proprietary, and the standard, the link layer discovery protocol. They both do the same thing, but one of them is Cisco proprietary, only going to work on Cisco devices. The other one is going to be a standard, which works in a multi-vendor environment. Layer 2 of Cisco devices only. It is a layer 2 protocol. Advertises the device information to the neighbors through a multicast when we do those things. And what do we see with it? Bring my handy dandy packet tracer over here. We can see a lot of information, and I've got this one set up because I've seen this question that says, hey, I've got all these devices out here, they're all connected, and we're connected together to a switch. Why do I only see the switch? Because from this device, from this 2911, because it's the only device that it actually is connected directly to. The other ones, it goes through the switch. So if I do a show CDP neighbors layer 2 protocol, it says, hey, I have a switch connected on gig 00. The whole time here is how long we're going to have to wait before it's going to time out. Capabilities of switch, it's a 2960, and it's on port, it's gig 01. We can show even more information with the show CDP neighbors detail. We get a detailed look at this thing here. It's a Cisco 2960, gig 01, and the software that it is running. That can be significant because if there are holes in the software, if it hadn't been upgraded, vulnerabilities in the software, then we could be able to find that here to do that. But we only see this one device because it actually is the only one it is directly connected. Let's go to this router 2 up here, this 2811 here, and do the same thing. Show CDP neighbors, and I see the switch and the router. And it's a 2960 switch and a 2800 router, and then the interfaces that we're connected on. The detail here gets kind of interesting. CDP neighbors detail. When I look at the router, 2800, Fast Ethernet 01, the version that it is on, let's see, the detail, outgoing Fast Ethernet 024 version, router, outgoing. The reason I am looking at this thing is it's not updated because it should be showing me the IP address. Or maybe I messed up the IP addresses on them. Show IP, brief, can't spell brief. And it says that I have one, ping 192.168.1, 3. And it did that. And let's see if it'll CDP neighbors detail. Still not showing me the detail that I want to see. We should also be able to see the IP address of that router. We've got a device ID, a router. Entry addresses, and again the IP address should be showing up here unless I have done something that would maybe turn it off on the other one. Let's see if CDP is running over here. There are a number of CDP neighbors, and it's working, and let's see if it will tell me detail, and it's still not showing me, but again we should be able to, and it'll probably start working about the time that I fast Ethernet 00. Be sure that I have the address on the right one. Okay. You have to trust me on that one. You should be able to see the IP addressing, see all of the information about that device. I'll let this run for a while and see if the and sometimes let me get out and back in, and then I will if I can get it to working right, I'll bring it back over to do these things. But the address list, the device identifier, the interface identifier, the address list, the network, and the data link address is going to be listed there. The platform capabilities and the advanced TLVs, type length values. These are blocks of information that are going to be available there. So it's going to show us a number of things that are available on the device. The IP addressing I always thought was kind of interesting. You can turn it off. You can turn it off on the entire device with the no CDP run command. You can turn it off on an individual interface, no CDP enable. CDP is one of those things that you really do need if you're using Cisco IP phones, because it gets its configuration information using CDP to discover the devices that have that information. So we have the show CDP neighbors, which gives us a summary, and then the CDP neighbors detail, which gives more information about what goes on or what is going on the device itself. We have the shows no CDP, and then the CDP. What shows up down here, CDP neighbors. We get the list, and then the detail, and this one has got the correct information in it. The device, router 100, the device ID, the name of the device, the IP addresses that is on it, the platform, the router, the interface that's on it. The whole time is how long we have until we have a timeout on the device. That which no longer there will drop it out of the listing. So this one actually does show what it should be, show CDP neighbors in detail, which gives us all of that information, detailed information about the device itself. Different commands, CDP enable, enables or disables that are no CDP enable on an interface, and the CDP run or no CDP run enables it or disables it on a device. It is on by default on all Cisco devices. Is it a real threat? Could be, because where are you advertising this information to is what you would look at. Somebody's got to be able to get onto one of your devices in order to be able to do that. you probably don't want it running on the interface that goes to your ISP, for instance. So you may want to do a no CDP enable on that interface so that you're not sending that information out of your network. It's something that is very useful, can be used to discover the topology of the network, can be used to discover the devices, a lot of things that goes on the network that are available to it. And another little lab here. The standard that can be used, the 802.1 AB standard, is Link Layer Discovery Protocol. It does the same thing as CDP, except it can be used in a multi-vendor environment. It's not Cisco proprietary, not Cisco specific. Works on Cisco and non-Cisco devices. It actually, the way it works is a little bit different, but the effectiveness is the same thing. Allows the discovery of devices running different protocols. It's disabled by default. It has to be turned on these Cisco devices. Each interface can discover one neighboring device because we're discovering adjacent devices, directly connected devices. That's why, one interface discovers one neighbor when we do these things. Advertises the status and the capabilities with the LLDP attributes, TLVs, and the TLVs, the system description and capabilities, the iOS that it's running, the device identity, port description, port VLAN, configuration information are all things just kind of like similar to same information, same basic information that we found in the CDP neighbors. The summary here, command summary, the interface, CDP, the interface, the way we configure it, CDP enable, no CDP enable. LLDP is a little bit more precise because we can configure it as a transmit or a receive or both, to do both of these things. The global configuration is CDP run or no CDP run, LLDP run or not. The default configuration on these, the CDP is global, the entire device. LLDP configuration is interface when we do it.